It's definitely used inside real-time schemes in terms of polling a suite of sensors for data and check for user inputs. Now this is opposite to interrupt-driven systems. Now, I'm not going to tell you that you should do or pull some scaling system based on pulled loops or on interrupt-driven systems. In the end, after the second lecture, we'll see that you really are looking for a hybrid solution where some tasks use this pulled loop strategy and other tasks may use an interrupt-driven strategy. So what is an interrupt-driven system? So here we will have a hardware signal that indicates that initiates an event. So once you receive it, the processor wants to complete the instruction being executed, so the exact same thing that we have been talking about before. Save the program counter so that you can go back later on once you're done with handling the event. Loads the program counter with the location of where the interrupt handler is located, the ISR, right? And then executes the interrupt handler. So now in practice, real-time systems can handle several interrupts at the same in a priority fashion. That's what we have seen. We see this interrupt table, and you see many possible interrupts that you can handle. And the reset interrupt has the highest priority. Then the external interrupts come in, and so on. Now you can enable them or disable them by setting the appropriate registers. And of course the highest priority interrupts are served first. Now the processor must check for interrupts very frequently. That is what I've explained, right? So it goes around checking all the flags that may have been set due to events that the hardware has registered. And once something is registered, it should immediately be able to switch to the interrupt handler. And the processor really repeats the run operation, check interrupts, if interrupts, then suspend task and run the ISR. So again, so with an ISR, it's a program that runs in response to an interrupt. What does the ISR itself do? It disables all the interrupts. It clears the interrupt flag that got it called, runs the code to service the event, re-enables the interrupts and exits to the processor so that it can go back to its running task. Now this should be done as fast as possible because once you have disabled this, you're sort of not listening for other interrupts anymore, right? So that's of course something that you would like to keep track of. So your interrupt handler or the ISR code itself should not have too many instructions that take too long. You cannot do that. Alright, so interrupts can be prioritized. So that is one thing that we note here. So service some interrupts before others when they occur. They can be disabled. They can and so meaning that the person does not even need to check for the hardware events that would otherwise have called those interrupts, and it can be masked. The processor only sees some of the interrupts. So here is one example of an interrupt-driven software system. So let's have a look at this one. So here we have a receiver that sees a threat and interrupts an aircraft mission computer to sound a cockpit alarm. So that's one element to this whole system. There's an internal navigation unit so there's internal navigation unit data that needs to be processed. So there's some velocities that the aircraft may have. And the data is available at a certain frequency, so it is being refreshed at that frequency and interrupts the navigation software with new data when it is ready. So it's very important because once there's new data, you may want to make sure that the navigation software updates its, the way the airplane flies. Then sonar contact data interrupts the signal processing software when new data is available. So when something comes in that's new, then an interrupt is being generated. And then there's, for example, a low altitude indicator that triggers a fly-up command for a pilot. So, as you can see here, you show a bunch of examples that can all be combined in one larger system that are all interrupt driven. So what I've done so far is really giving you a quick overview of what operating systems do, how real-time operating systems are different from actual operating systems that are very complex, and we've been talking about polled systems, like we are polling data, and then based on once, for example, I poll the ready flag in my UART get string, right? So when that ready flag is equal to 1, so I poll that all the time. Once it's equal to 1, I will execute the task accordingly. So meaning I will interpret the string that I've received, as an example. And the interrupt-driven methodology really corresponds to the ISRs that you have been writing. So in a larger context, so the next lecture actually, we will talk about other elements that make up an operating system, and also the other scheduling policies that are a little bit more, that are different, and hopefully will be very interesting for you. So that's sort of the leading to real-time operating systems. And then next semester, obviously, we will be talking a lot more about real-time operating systems and give you lots more insight in how that works. So it's very exciting. So if you're thinking as an engineer, right, as a hardware engineer, how can I really work later on in industry? Well, you will be working in a team. Nothing is pure hardware, nothing is pure software, it's all a hardware-software co-design. So you need to understand the language that your colleagues are talking in. And that goes both ways, obviously, so that's why it's a great idea to not only know about how you program the MCUs, but you will also start figuring out what kind of operating system, real-time operating system would you actually like to have in your system. You can discuss that in a sensible way. Not that you're an expert in it, but at least you are able to engage in a sensible discussion, and through that come up with really good decisions. And that's really what team efforts are all about. And usually the team is much larger, right? Someone is an expert in certain type of peripheral or whatever it is, so we will have a large team that can interface with one another. But for you it's very important to really understand how a complex system can be built. And it will use a real-time operating system. So, and of course next semester we'll be going through a much more complex assignment, effectively, one big project, like the assignments accumulate in one big project, where it makes sense, or I would like you to actually use a real-time operating system that you can just download, or it's open source, that you can then just use. So hopefully those of you who will continue will have that experience and feel that's worthwhile. Alright, so any questions about this part, and then we can go to the laboratory and you guys can start with your assignments. Any questions? How many of you have done operating systems at some point? No, a little bit? Also a little bit? Yeah. Well, I hope that the next lecture will be kind of interesting, because I mean, how can you create this virtualized environment that seems as if all these processes are all sharing the same, are all using the same resources at the same time, which obviously is not the case. They alternate, but how can you do that in the most efficient way? And if you context switch too often, you need to do a lot of bookkeeping. And also bookkeeping means that you're wasting process cycles. So how can you find the right balance? Anyway, pretty cool stuff. Alright, so let's go to the lab.